Okay, now let's do our third and the final step. We prove the filtration theorem. We will prove this by starting from the right hand side. Now let's look at the definition of ek, 0 sub infinity. Okay, so here's the definition for e sub k, 0 sub infinity. Let's make two observations. First, let's look at this term, sk0 infinity. By exercise 1.7.h part C, this guy is actually equal to, this term is equal to the kernel D, where D is from e sub k to e sub k plus 1. So actually, we can verify this in here. So sk0 will be same as ek. And this infinity means a k0 strip can be knocked by D infinitely many terms into the filtration, which means it can be killed by D. So this guy is equal to the kernel of D. And now let's look at this term. What's this? We notice that this guy is actually contained in ek, and ek is equal to the set of k0 strips. At the same time, this is a collection of boundaries, which means they can be killed by D. So this guy is actually contained in sk, 0 sub infinity. So this term will be equal to D of ek minus 1. And we will left this term untouched. The same argument as before, using the isomorphism theorems, shows this term is a quotient of this guy. So noticing that this is the cohomology, we have shown that ek, 0 sub infinity is a quotient of the cohomology. If we denote this arrow, this epimorphism by pi sub k, and we let f sub k minus 1 to be the kernel of pi sub k, which is a subset of the cohomology. So we get this embedding. And the cohomology modulo this kernel is isomorphic to ek, 0 sub infinity. Actually, one can write this out explicitly. The kernel of pi sub k will be equal to this sum modulo this boundary. So we have made our first step in proving this filtration theorem. We have proved this part. And now let's continue. This is the formula for ek minus 1, 1 sub infinity. The same argument as before shows that this guy is a quotient of this part of it. And now, by using an isomorphism theorem, this guy, see this intersection, is isomorphic to this guy. The sum of dek minus 1 and sk minus 1, 1 sub infinity modulo dek minus 1. But this is precisely fk minus 1. You see from here? Okay. So ek minus 1, 1 sub infinity is a quotient of fk minus 1. And now we compute the kernel of pi k sub 1, pi k minus 1. It equals to this guy modulo this guy. Okay, now we define our fk minus 1. Oh, sorry, fk f sub k minus 2 to be this kernel. Now we have made the second step in the proof of this filtration theorem. Now we have proved there's a filtration like this. Now let's continue. Okay, now let's look at E sub k minus 2 comma 2 sub infinity. By the formula we got for this, it is isomorphic to this quotient of s k minus 2 comma 2 sub infinity modulo this intersection plus this term. Now we made the same observation. We observe that this guy is a quotient of this part of it. And again, we use an isomorphism theorem to transform this piece into, sorry, this should be a comma 2. To transform this thing into this, the quotient of d e k minus 1 plus s sub k minus 2 comma 2 sub infinity modulo d e k minus 1. I'm sorry, there's a typo. This map should be denoted I sub k minus 2. So once we get an isomorphism, we wish to show that this guy is same as f sub k minus 2, because once this is true, we get one step further about this filtration theorem. We will get f sub k minus 2 modulo the kernel. So this fk minus 2 as before will be defined to be kernel of pi sub k minus 2. Fk minus 2 modulo f sub k minus 3 will be this guy. This e sub k minus 2 comma 2 sub infinity. To this end, let's recall the definition of fk minus 2. Here's the definition of fk minus 2. So we notice that they look quite similar. So, but in here we have intersection with s sub k minus 1 comma 1 sub infinity. So now let's construct an isomorphism from here to here. This f sub k minus 2 is defined in the following way. We first observe that there's an embedding from here to here. This is an inclusion map, and this inclusion map will send this denominator into this denominator. So there's a well-defined natural map from here to here. So f sub k minus 2 is reduced by this embedding. Now let's show f sub k minus 2 is an epimorphism. It is surjective. This is because if we take an element from here, where A is taken from e sub k minus 1 and B is taken from here, infinity k minus 2 comma 2 strip. So the equivalence class this element is living in represents for an arbitrary element from here. Now we want to find an element in here that can be sent by f sub k minus 2 to this, the equivalence class of this element. Now we consider this equivalence class, and we apply f sub k minus 2, and we will get since fk sub 2 is induced by embedding, we will simply get e plus dE sub k minus 1. But we know this equivalence class is same as this equivalence class. dA plus B plus dE k minus 1, because d of A is already in here. So this element will be the equivalence class this guy is living in. Now let's show f sub k minus 2 is injective. To this end, we compute the kernel of f sub k minus 2. The kernel of f k minus 2 will equal to the elements in here that are mapped to here, modulo this guy. The elements in here that are mapped into here will simply be the intersection of this guy with this guy. We need to modulo this guy by this. So this is a kernel. And now let's simplify this ugly quotient. We first apply the distribution law of the intersection, which is ek minus 1 intersection sk minus 1, 1 sub infinity plus this guy intersection s k minus 2, 2 sub infinity modulo the first summand. And we observe that this s sub k minus 2, 2 is contained in this. So this term can be absorbed into this. But after we remove this guy, we see the numerator and denominator are the same thing. So this guy is trivial. It's a trivial module. So we know the kernel of fk minus 2 is trivial. So fk minus 2 is injective. So now fk minus 2 is an isomorphism. So this gives us the third part of the filtration. When they are isomorphic, we can identify fk minus 2 with this guy. So we can think of a kernel of this contained in f sub k minus 2, so that if we let f sub k minus 3 to be the kernel of pi sub k minus 2, then f sub k minus 2 modulo this kernel is precisely this guy. So we will repeat this argument over and over again to get the filtration. And in general, we will define f sub p to be the quotient. This is the definition of f sub p in general. It is defined to be the intersection plus s p comma k minus p sub infinity modulo this intersection. And we will also have f sub p modulo f sub p minus 1 isomorphic to stabilized p comma k minus p object in the spectral sequence. In particular, let's look at f sub 1. f sub 1 is a quotient, the sum dE k minus 1 intersection s2 k minus 2 sub infinity plus and s sub 1 comma k minus 1 sub infinity modulo this intersection. Now we want to show that the quotient of f1 modulo this e0k infinity is the same as 1 k minus 1 infinity. By the formula, E1, k minus 1 sub infinity is defined by this quotient. Oops, this should be S1, k minus 1 sub infinity. And this guy, similar to what we have done before, is a quotient of this part of it, which by isomorphism theorem is isomorphic to this quotient. But this quotient is actually isomorphic to S1. This is by essentially the same argument as we have done in here. So this is isomorphic to F1. Next, we compute the kernel of pi 1. By definition, the kernel of pi 1 is equal to the quotient of this guy modulo this guy. However, we notice that by essentially the same argument as in here, this quotient is isomorphic to this quotient, which by the isomorphism theorem isomorphic to this guy. But by definition, this guy is precisely E0 k infinity. Because if we see this is definition, let's plug in p equal to 0 in here. Then this will be s negative 1, comma something. But this negative 1 doesn't make sense because once this is outside of the first quadrant, this term will vanish. A negative 1 k plus 1 strip will be just 0 strip. So therefore, by definition, this quotient is just E0k sub infinity, and we have shown that kernel of pi 1 is k0 E0 k infinity. F1 modulo kernel of pi 1 is precisely E sup 1, k minus 1 sub infinity. So now we have that. So let's review this proof. The key idea in this proof is to look at the denominator in each definition of E sup pq sub infinity. And in each step, we will drop this summand. You see here we drop it, and here we drop it. We get something whose quotient is this E infinity. The quotient of this is E infinity. And we use the isomorphism theorem to transform this intersection into sum. And meanwhile, there's a crucial isomorphism between this guy and this one. The previous f sup something we defined. And in each step, f will be defined by kernel of pi something. And we repeat these procedures inductively, and we get the filtration.